Welcome students, we are going to start up this class by learning about Leibniz rule, and it is rule number 1. Now the definition of Leibniz rule number 1 is given as follows: d over dt integral a to b f of x comma t dx is equal to a to b dou f over dou t times dx. So this is the Leibniz rule number 1. Now the most important point that we will have to note here is a, b are constants. Now I'm going to show you the proof for the Leibniz rule number 1. So let's do this. So foremost, what I wish to do is let us consider I of t to be equal to integral a to b f of x comma t times dx. So f is a function of two variables, x and t. Yes, you have heard it correctly. X and t are both our variables. And if we were to be given a function of this fashion, how are we going to integrate? So that is the biggest quest. It is imperative to understand that not all functions are integratable. Say for example, you are given integral 0 to 1 e raised to the power of x times dx. This can be integratable into an elementary function. So if I were to integrate this is going to be e raised to the power of x, right, within the limits 0 to 1. This is always possible. But if in case this is little bit changed, say for example, let me give you this illustration. Say for example, instead of this, if we were to be given say 0 to x e raised to the power of negative u squared times du, you cannot simplify this using elementary functions. It's just not possible. Of course, you can use the power series expansion for e raised to the power of x, or in this case it's e raised to the power of negative u squared, but it is just not possible for us to simplify it via elementary functions. So that is why we need the help of Leibniz. So having mentioned that, let me just go on to show you the proof. So I'm considering this I of t to be equal to integral a to b f of x comma t times dx. Now let me differentiate this quantity. So differentiating this with respect to t, it's total differential. So d over dt of I, right? In this case it's I of t. Now if I were to apply the differential, or in other words the differential operator, to this function, then by definition I can rewrite this to be as limit delta x tending to 0 of I of t positive delta t negative I of t divided by delta t. Now where am I getting this? This is nothing but the popular definition of derivatives, where you would have seen such a explanation for differential, say limit h tending to 0 f of x positive h negative f of x divided by h, using the first principle where h is tending to 0, right? So we are exactly using this first principle and representing d over dt of I of t. Now I of t is integral a to b f of x comma t dx. So therefore what is I of t positive delta t? What is this? Let me write this down. We know that this is going to be equal to integral a to b f of x comma, in place of t I've got t positive delta t. So this is going to be t positive delta t times dx, and I of t is integral a to b f of x comma t times dx. So if I were to take this as 2, therefore I can rewrite 2 to be as limit delta x tending to 0, I'm going to place delta t like this. I of t positive delta t is integral a to b f of x comma t positive delta t times dx negative integral a to b. I of t is f of x comma t times dx. This is what we've got. Now of course I can rewrite this further in this fashion. Limit delta x tending to 0 of, I can split this as integral a to b. I can club these two integrals in this fashion. F of x comma t positive delta t, this is one component, minus f of x comma t, this is the second component, divided by, I can push delta t inside, so this is what I've got. Now let me place this in square parenthesis and multiply it by dx. Now I want to push delta x tending to 0 inside, so this is equal to integral a to b limit delta x tending to 0 of f of x comma t positive delta t negative f of x comma t divided by delta t. Now this is placed inside the parenthesis with dx being outside. Now what is this? This is the explanation, or this is the exact meaning for a derivative, right, using limit concepts. So since I have two variables x and t, I cannot use total differential, so I will have to use partial differential. So since the given function is f, so it's going to be dou f over, the increment is occurring for t, so this has to be dou f over dou t, right, with the integral sign a to b and the operator dx. And what is this? This is exactly what we started with, right? This is the Leibniz rule, and hence proved. So this is a powerful concept, and we would apply this concept in solving complicated questions. Students, we are given a beautiful question. So the question is as follows: given g of x is equal to integral 1 to 2 cos t times x over t times dt, and we are asked to find g dash of pi. Now you might be thinking of integrating it and then finding the value when you differentiate the function and then subsequently substitute x is equal to pi. So that is not going to be an easy task because we got two variables x and t. So we need to apply Leibniz rule number 1, because there is also rule number 2 which we would be also studying in a later lecture. So what I wish to do is I would be differentiating both sides. So if I were to differentiate this with reference to x, so it's going to be differentiating both sides with respect to x we get. So this is going to be d over dx, total derivative of g of x is equal to d over dx integral 1 to 2 cos tx over t times dt. By Leibniz rule, if this d over dx goes inside, it becomes partial derivative. So this is equal to integral 1 to 2 dou over dou x of cos t times x divided by t, and you have dt there. Now in this case we have to differentiate x keeping t as constant. So that in turn would give us, let me write that down, this is equal to integral 1 to 2. When I differentiate cos tx, it's going to be negative sine t times x. Of course I have to retain that t there, and the coefficient of x in this case is t, so place that t and you have the dt there. I hope you are following me. So clearly what happens, you see, that's the beauty of this Leibniz rule. The t that is giving us complications is now being removed. So now what have we got? We have got, let me use the space over here. Right, so this is equal to integral 1 to 2, negative sign, I can place the negative sign out. And you have got sine t times x. And you have the operator dt there. So now we can integrate. Now this integration is done with respect to t, and x is kept as a constant. So we have no issue with that. So if I were to integrate sine t, there is going to be a presence of a negative sign. That negative sign will get neutralized by this negative sign. So coming back to the integral of sine t, we are going to get cos t times x. Now the coefficient of t is x, so I divide by x, and the limits are 1 to 2, so there is no change in the limits. So the limits have to be applied for t because the integration is done with reference to t. So if I were to apply the limits, this is going to give me cos 2 times x negative cos x divided by x, right? And what is this? This is my g dash of x. So this is my g dash of x. But we are expected to find g dash of pi. So when x is equal to pi, we are expected to find g dash of pi, which is nothing but, I substitute pi here, cos 2 pi minus cos pi divided by pi. Cos 2 pi is positive 1, cos pi is negative 1, so negative of negative will be positive, right, divided by pi. So this is going to give me 2 over pi, right, and I can state that to be the answer, 2 over pi. So that is a good place for us to draw the red line. So this is a beautiful question, students. I hope you understood this question, and we will move on to the next question, though it looks a little bit challenging because of the presence of two variables, yet with the Leibniz rule number 1 we were able to achieve the outcome. So we will move on to the next one. Students, we are given a beautiful question. We are expected to integrate integral 0 to infinity dx over x squared positive a squared raised to the power of 2. We have to get the outcome for this. Now this is x squared positive a squared raised to the power of 2. So it is imperative that we adopt some caution. Now what I wish to do is, I would like to use the following result. We already know that integral 0 to infinity dx over x squared positive a squared is equal to pi over 2a. We know this result. In fact, it's straightforward integration, and by that means we will be able to simplify this using elementary function, and subsequently upon substituting the limits we would get the value pi over 2a. That is the simple understanding. Now having got that understanding, let us go and use Leibniz rule. Only with Leibniz rule, in fact Leibniz rule is the shortest way by which we can simplify this and extract the solution for this question. So I'm going to state that by Leibniz rule number 1 we know that. So what do we know? We know that d over dt, its total derivative, integral a to b f of x comma t times dx is equal to integral d over dt is pushed inside, it becomes partial differential dou f over dou t times dx. Limits are a to b. So this is the important result you will have to keep in mind. So I will be using this result. So let me just take this as 2. So let us consider 2. So what is 2? 0 to infinity dx over x squared positive a squared is equal to pi over 2a. Now x is the variable, a is also the variable. That's the way I am treating it. So what I wish to do is I would be differentiating both sides with reference to a. So differentiating both sides with respect to a, we get, so what do we get? This is going to be d over dA integral 0 to infinity dx over x squared positive a squared is equal to d over dA of pi over 2a. Now I push d over dA into or inside the integral, so that would be 0 to infinity dou over dou a of, I'm going to write this quantity in this fashion, 1 over x squared positive a squared times dx. So this is how I am representing the quantity. Now d over dA of pi over 2a. So let me just show you the working here. So this is d over dA of pi over 2a. Pi is a constant, 2 is a constant. So I can take pi out, I can take 2 out. So I get d over dA of 1 over a. Now I can rewrite this as pi over 2 d over dA. 1 over a I can take it to the numerator. So it's a raised to the power of negative 1. So this is pi over 2. I differentiate this, I get negative 1 times a raised to the power of negative 1, negative 1. This can be rewritten as pi over 2 negative 1 a raised to the power of negative 2, right? Which is nothing but negative pi over 2 times a squared. So this is what I get. So I can place that value here. Negative pi over 2 times a squared. So that's a nice value that we have got. So now we need to differentiate 1 over x squared positive a squared. So I would have to use, so let me use the space over here. So dou over dou a of 1 over x squared positive a squared. A is the quantity with which we are differentiating and x is constant. So this is going to be u over v formula. For those of you who would like to have a recollection, d of u over v is nothing but v times u dash minus u times v dash divided by v squared. So this is the formula we will be applying. So this is x squared positive a squared times differential of the numerator is 0 negative 1 time differential of this quantity. So differential of a squared is going to be 2 times a divided by x squared positive a squared raised to the power of 2. Now this is equal to negative 2 times a divided by x squared positive a squared raised to the power of 2. So this is what we've got. So let us club these two things together. So this goes here. So let me write that down. Negative 2 times a divided by x squared positive a squared raised to the power of 2, right? And I have a dx, don't forget that, and I have an integration sign. So the integration sign is 0 to infinity, and I got a negative pi over 2a squared. So all of these things are there. Now clearly what we can do is we can get rid of these two negatives there, and then we can push this to the right hand side, right? So if I were to do that, in fact I got a also, I can push everything to the right side. So this is going to be integral 0 to infinity dx over x squared positive a squared raised to the power of 2 is equal to pi over, I push this, I get 4 times a raised to the power of 3. Now what is this? What is this? This is exactly what was asked, right? And we have got the outcome, and this is a good place for us to draw the red line and subsequently to conclude. Therefore integral 0 to infinity dx over x squared positive a squared raised to the power of 2 has been found to be pi over 4 a cubed. So that's a good place for us to stop, students. So this is Leibniz rule number 1. In the subsequent lecture, I would be dealing with Leibniz rule number 2, which is a little bit advanced than this. So having mentioned that, I would like to request you all to review this, practice this, and then subsequently follow the step 1 and keep repeating until you get the mastery of this topic. Thank you very much. Have a good night.